Hello, Professor. This is my submission for CISC 16 Assignment 4. Let's quickly go over the question. Um, the main objective is to develop a linked heap data structure, which has functions to insert, delete, uh, peek, and based on that linked heap data structure, create a priority queue data structure, which has methods to add a node, remove, find the minimum, check if the data structure is empty, and also the length of the uh, priority queue. Once we create these two data structures, the final task would be to prove that these two data structures work. And the task is to enqueue the following items. There are seven keys that are supposed to be enqueued to the data priority queue, and dequeue three items based on priority. So let's move over to the code. Uh, so we're first importing binary node from the file that is. Let's quickly look at binary node. Uh, Basically, the binary node, when initialized, contains the element parent node, left and right child, and it has methods to get the element, get parent, get left, get right. And there are also methods to set an element value, set the parent, set left, set right. One thing to note is that this all these set functions will work only if the value is currently none. Moving on to the linked heap code. We'll go through the code from top to bottom so that it's easy to understand. Um, so first we are declaring a class called linked heap. Um, we are initializing it. As a part of initialization, we set the root as none, and um, we have the size as 0. Every time we enqueue, we increase the size by 1, and every time we dequeue, we decrease the size by 1. This way we can maintain the length of the queue. It's important to maintain the length of the queue because we insert and remove the nodes based on we determine what nodes to insert to and remove based on the size of the queue. Uh, the next function is index to binary. This is a helper function which basically converts the index, which is an integer value, into a binary value and returns the binary value. Um, this is to determine, basically we use this helper function to determine if the left node is if the left or right node is empty, and insert on that left or right child. The next function is to swap two nodes. Basically, it takes two nodes as inputs. In our case, usually in a heap, we might have to oftentimes swap the parent and child. Uh, so we use this node swap method to swap the parent and child here. How this works is initially it gets the pre-parents left and right. Um, to determine if the parent is on the left side of the node or right side, and based on that it swaps with the child node and uh, returns basically the swapped nodes. The next method is the float node. Float node is basically a method which is used to float a node to its appropriate place. So when we insert a new node into the when we insert a new node into the heap, we usually put it at the bottom most available slot, and then this float node compares the node that we inserted with its parent and determines if it has to be swapped or not. And this happens recursively until the node is in its current place here. Uh, the next function is the min node. Before going to min node, let's go to the sync node. Sync node is basically the opposite of float node, where float node moves a node from bottom to the top based on the key value. Sync node uh, brings or puts a node in its appropriate place from top to bottom. Uh, so that's basically a sync node. The sync node uses a helper method called min node, which determines if the left node or right node is the minimum of the nodes. We use it to determine if a node has to be in a left or right hand side position. The float node and sync node are called when we insert or remove, when we do an insert, NQ or DQ, or insert or delete into the structure. That's where we call, when we insert, we call the float node so that we can move to the appropriate node. And when we delete a node or DQ, we call the sync node, which basically moves the new node in that place to its appropriate position. Path to node is also a helper function. It basically returns the parent node. Moving on to the insert node. The insert node takes two values, which is the key and the value. If no value is given, then it is by default set to none. Um, we leverage the binary node which we imported to create a node. Uh, if the heap is empty, that is determined if the self.root is equal to none, then we set the root as the binary node. Else we create a node and determine what the parent of the node is to be, and also based on the size we determine which node, which side of the tree, either left child or right child, the node has to be added. If we determine if the left child is none, if the left child is none, then the new node is put on the left hand side. If not, it is put on the right hand side based on the availability. And then we call the float node function, which compares the node to its parent recursively and puts it in the appropriate place. Next is the delete node, which basically returns or removes the root node and or returns the root node and rearranges the tree appropriately once we remove the root node. So how this works is first we get the root element, which is stored in my item that is supposed to be removed, and then we determine the element, the last node, which we usually use to swap the root node with. So once we determine what the root node is, we determine the last node and set the last node to none, remove its left and right childs, and then we replace the root node with the last node. Once we replace that, this is where we do it. Where we set the last node as the root node after removing the root node. Once we do that, once the last node is in the root position, then we call the sync node function, which compares the root node with its childs, both left and right, and determines if if that node has to be swapped with either of those. So this happens recursively until the last node is in its appropriate position, and this function also returns the root node as an output. The next function we have is the peak, which returns the root without removing it from the structure. Length method returns the size of the heap, and we have two string methods to print out the data. The next part is we define a priority queue. Most of the functions are derived from the heap structure above. As a part of initialization, we declare, we create an object mypq, which we declare as a linked heap. For NQ, we are basically leveraging the insert node method that we defined in the linked heap. And for DQ, we are using the delete node. For the minimum of the queue, which basically returns the minimum value in the queue, we use the peak. Length of the queue, we use length, and based on the length, we also check if This is a method to check if the queue is empty or not. Moving on to the main function here, we create an object myQueue, which is a priority queue. Um, First thing, we check if the queue is empty. Since we just initialized it and there is no data in it, this should return as true, and the length of this queue should be 0. And then we start enqueuing elements. We enqueue one element after another, so 7 elements. And then now we check if the queue is empty. In this case, it should be false because we have 7 elements in it. The length of the queue will also be returned here. The next step is to dequeue 3 elements from the queue. Every time here we are calling we are first peeking into the structure to see what's the minimum element, and then we are dequeuing it. The same we repeat it 3 times, and then we check the length of the queue. Let's run the code. Here we see that initially when the queue is initialized, it's an empty queue. The length is 0. And then we are adding elements to the queue. We see a print statement here every time we add an element. Next, when we check if the queue is empty, it returns false. It also returns the length of the queue is 7. Now we are dequeuing elements, and here we see that the first element we are removing is 4, which is the smallest of the list, and then 5, and then 6, since we did not give any priority due to any of them. The least the value the least key values will be returned 4, 5, 6. Now the length of the queue is 4 since we removed 3 elements from 7. That's it for this assignment. Thank you.